Required practical 2 is investigating interference and diffraction from double slits and from diffraction gratings. Ideally, you'd do this in a very dark room, and we are somewhat stymied in this room because although we have blackout blinds on all the windows, we have them on all the windows except those skylight windows. So unfortunately, it's about as dark as I can get this room. But that's okay, we'll do the best we can. Now, in terms of equipment, what we're going to use is these diffraction gratings with different numbers of slits per millimetre, 300, 600 and 1200, and these double slits with a separation of 0.1 millimetres, 0.5 millimetres and 1.0 millimetres. And we're going to use 3 different colours of lasers. We're going to use red lasers, we're going to use blue lasers, looks a bit purple in this camera, and we're going to use green lasers. And you'll notice I'm just using these cheap laser pens that you can buy for about £1 each off eBay. There are some issues with these, things you have to be careful of. You really shouldn't be using lasers with a power greater than 1 milliwatt, and although these claim to be 1 milliwatt lasers, the likelihood is they are more powerful than that. They certainly look brighter than 1 milliwatt. So you do have to be very cautious with these. You can put filters in front of them, or you could just be extra cautious. Obviously, risk assessments are very important here. The other thing to be aware of, you see, that is definitely a red light, and I'm not sure if you can see what it says on here. It says 532 nanometers. There is no way, I think that says 532, my eyesight is failing me. Let's zoom in. 532 nanometers. It says less than 5 milliwatts. Well, it should really be less than 1 milliwatt. But I don't trust what it says on the label, because there is no way that this is 532 nanometers. It's red. 532 is green. So even though the label says that it is red light, it's got a little red arrow there maybe, although maybe that's not what that little red arrow means. There is no way this cheap made in China laser is actually, the label is correct. I mean, it's blatantly not correct. The blue one, less than 5 milliwatts, it says 405 nanometers, plus or minus 10. That is blue, and it's got a little blue arrow. So maybe that arrow is supposed to indicate the colour, because this is the green one, and it's got a little green arrow. See, that's got a little green arrow, so that's encouraging. And this is 532 nanometers as well. Again, it says less than 5 milliwatts. Really ought to be less than 1 milliwatt. Now, with all practicals, we should start by considering our variables. Now, I would suggest, excuse me, I would suggest that because we have 3 different colours of lasers, we could make the wavelength lambda a variable. And then we can see the effect that that has on, let's say, W, the fringe spacing, or over here on theta, the diffraction angle. That would be good. But you've also got different slit separations and different numbers of lines per millimetre. So different S's and different D's. So that could be the independent variable. And we could increase the number, the distance between the slits and the screen, which is D, or decrease that. So that could be the independent variable. Or down here, we've got multiple different orders that we could investigate. So N could be the variable. So we've got to be clear what it is our variable is going to be. So before we decide what our variable is going to be, it's worth doing some preliminary tests just to see what we can see on our screen. And that will help us decide whether it's reasonable, for example, to have the 3 different slit separations. Can we actually see the fringes from the different slit separations? And if we can, then that could be the independent variable. We also have to think ahead. We're doing an investigation, and we want to have to find something out. And quite a nice thing to have to find out might be lambda. Because as we know, it's written on the lasers, but we know it's wrong, especially for the red laser. So we could do some research to find out what the wavelength should be of these cheap laser diodes of these colours. They're going to be the cheapest that you can get of these different colours. And we could use our spectrometer to work out what those wavelengths are, although shining a laser down a spectrometer is a really bad idea, but we could do something. We could set something up so we could measure the wavelength using a spectrometer. So we could do that, or we could do some research, and then we've got something to reference. Now with the slit separation, S, and with D, we can trust what it says on the diffraction grating, or we could get out a travelling microscope and see if we can measure it. So there's a lot we can do here. Let's start with some preliminary tests to see what's reasonable. So this is where the experiment is going to be done. Over there, I'll put the screen on the wall. Over here somewhere, I'll put the slits, and I'm going to use this simple clamp stand to switch the lasers on. What I'm going to do with this clamp stand is I'm going to use the clamp part. Let's just take it out to show you. I'm going to use the clamp part here, place the laser in it very gently, and then close the jaws. And when you close them just enough, the light comes on. So you can see when I close it just enough, the light comes on. And then I don't close it anymore, or I'm going to damage the switch. Now I've got to be careful. I don't want to shine the dot at anything which is shiny, and I want to make sure that the beam remains horizontal throughout. So that's why it's going to be so important to clamp my laser in place. Something like this. Another thing that you can do for safety, because there's going to be, let's just move this like this so you can see where I've clamped the laser, or I'll just move the laser actually. The other thing I need to think about is I'm going to get some light reflected off my slits. I'll show you. If I just take any one of these slits and place it in this very crude slit holder here, and then arrange it so that the light is illuminating. Grip it. There we go. Move this down a little bit. Illuminating the slit like this. There is light being scattered backwards from that slit. Let me show you. Let's just take the camera for a walk. So we have our laser clamped loosely here to turn it on, and yet here we've got our slits. And if I hold my hand, just sort of maybe have a look around, there it is, can you see that I've got light reflected back towards the laser? Now that actually is nearly on the laser, but not quite, which shows me that I don't quite have this lined up properly. But nevertheless, I'm clearly getting light reflected. Now, if I look to the other side of the room, there it is. And it's a nice vertical line, which is a concern, because if I'm stood over here doing an experiment and I turn around, then I might get an eye full of laser, which I could really do without. Let's see if I can put the phone in such a way that I get a rather nasty eye full of laser. Well, you can start to see it there. Now, we do have to be careful, particularly with the green laser. The green laser also emits a significant amount of invisible electromagnetic radiation, which we have no blink reflex to. Always turn it off when not in use. But because of that, we could get light reflecting off, scattering off. We can't see that could cause damage to our eyes. That's not the case with the blue and the red, but definitely is the case with the green. So we do need to be careful with these. Now, we don't have special eyewear that filters out infrared or ultraviolet. We don't have that. So there's no point even thinking about wearing safety goggles or anything like that. We don't have them. So we've just got to be extra careful. Well, the make, do, and mend attitude of physicists knows no bounds. Here's an old box. So I could put this box positioned behind the laser in such a way that any light that would be reflected back gets absorbed inside that box. And that's just going to make it safer for everyone. Something like this behind our experiment is a really good idea. Now, at no point am I going to place my eye in the laser beam. That would be incredibly dangerous. So I always keep my eye above the plane where the laser is. And there we have it. So I've got my laser here, I've got my slit here. At the moment I've got 0.1 millimeter separation. Let's have a look what I can see on the wall. On the wall I can see, yes, I can see I have got some fringes, and in this central region here, I can see the separation very easily, which is good. You can see that we lose some fringes over here, and that's due to the effect of single slit diffraction. The two slits each have a finite width, so we get a superposition of two interference patterns, the single slit diffraction pattern and the double slit diffraction pattern. Now you might think, let's use some vernier calipers to measure the distance between these fringes, and that's not a bad idea, except our vernier calipers are nice and shiny. So it would be incredibly dangerous to put them into the laser beam where we're now producing reflections. You know, you can see we're producing reflections, and they could go in the eye and they could cause eye damage. So we need to be careful of that. And that's why we've got this paper and this masking tape, because we're going to tape the paper up to the wall, and then we're going to draw on the paper where the different fringes are. But not right now, we're just seeing which slits actually are useful. So I reckon green and 0.1 millimeters, that works fine. Now let's have a look at green and 0.5 millimeters. Obviously you should turn the laser off in between. Okay, now that one, where this slit separation is 5 times as much. So because the slit separation is 5 times as much, we would expect the fringe spacing to be 1/5 as much. And we now can't see what we're looking for. You know, if we have a look at the diffraction pattern, that central fringe is so bright. You get some lovely sort of speckle on the wall. Anyway, it's so bright, we cannot... Actually, I don't think that is speckle. Well, it might be a projected image of the speckle. I think it is. Anyway, forget speckle. Speckle isn't on your A-level. We've got these central part here, and you can see perhaps 3 fringes. It's quite bright, though, and it's hurting my eyes, because this laser is too bright, really. So 3 fringes there in the middle that I can clearly discern. That's not good. That means there's just no point really doing an experiment where I look at double slits and I use the 0.5 millimeter slit separation over the sort of distances we're talking about. And I know, therefore, if I use the slit separation that's twice as much as that, which is 1 millimeter slit separation, and I plot that into our in the way of our laser beam, what are we going to get? We're going to get, forget about it, but I can't see it. I cannot see the double slit interference pattern from that. And I think that's obvious, I wouldn't be able to. So, you know, forget about it, that's just no good. It's actually slightly easier with less bright lasers sometimes, because you don't get so much glare from the middle, but we'll carry on. So preliminary test, is it reasonable to use different spacings of our double slits? No. There's only one we can reasonably use, which is 0.1 millimeters, in which case I'll put the other slits away, and we now know that the slit separation cannot be an independent variable. It just can't. Now let's have a look at diffraction gratings and see if we can get anything sensible from diffraction gratings. And I'm choosing the green laser, by the way, for 2 reasons while I'm doing these preliminary tests. Mainly because the wavelength of green is somewhere between the wavelength of red and blue. So if I can't see something with green, it's useless. If I can, then it's probably going to be likely I can see something with the red and with the blue. The second reason, perhaps the more important reason, is that the green light is easier for my eyes to see. My eyes are more sensitive to green light. That's going to be very helpful for me to see any small, very dim fringes. So let's have a look at 300 lines per millimetre. Right, that's nice. 300 lines per millimetre, I can clearly see a great number of orders there. I can use that with some basic trig to measure the diffraction angle. And that's 300. Now we can try 600. Yeah, look at that. 600, no problem. And then 1200, 1200 if you prefer. Yeah, absolutely fine. Again, be careful because you're going to get reflected diffraction as well as transmission diffraction. So you do need to maybe even put a box all the way around here to stop the reflections coming off the sides as well. But that'll be fine for us for now. We'll be able to make measurements with that. So in terms of variables, I have got different colours of the laser, therefore different wavelengths, different numbers of slits per millimetre, and different distances between the slits and the screen, different orders. They're all different variables I could have. You'll notice I've not used a single slit during this experiment. I don't need to. The single slit is to produce a coherent light source, but lasers produce coherent light already. So the only reason I might be tempted to use a single slit is to reduce the intensity of the laser, and if I'm going to do that, I'll just get one with batteries that aren't quite as good. So I don't need to worry about that. The variables then. Let's go back to what we were talking about. Okay, so taking this first one, S is not a variable. I'm going to draw a red box around that to indicate that that is a constant. So now we've got a choice. We could use different wavelengths of radiation and measure the different fringe spacings and use that to determine what D over S is, or S over D if we rearrange the equation, it doesn't really matter. And then we can measure what S is to check that our answer is fine. And that's good, we can do that. The problem with that, of course, is that one of these wavelengths we don't know. We know it's wrong on the laser. So perhaps we could use the bottom equation to determine what the wavelengths of the different lasers are, and then, or in particular, the red one, and then we use that information in here. And then, of course, we can do some research to check that that wavelength that we measured was actually correct. So that's the whole thing coming together. So what I'm saying there is, because we want to determine what lambda is, this would also be a control variable, but we are going to do this bottom experiment 3 times with different colours. And we could even do the top experiment 3 times. So there's 6 experiments in here. In terms of dependent variables, well, we could have theta as a dependent variable for different d's, or theta for different n's. Or, even better than that, we could actually rearrange this equation to have lambda equals d over n sine theta. And now what we can say is, this is a constant. Oh, I've rearranged that in a really dopey way. D over n, we could say, is our independent variable. So we're actually measuring 2 different things, and we're changing them. We could do that. So slit, and then n1, n2, n3, n4. Then a different set of slits, n1, n2, n equals 3, n equals 4. A different set of slits, n equals 1, equals 2, n equals 3, n equals 4. And then do that for the 3 different wavelengths for 3 completely separate experiments, measuring theta, or sine theta, as we go along. And then we can use that in there. That, I think, is sensible. So then in here, what's our independent variable going to be? We've only got one slit. We've got 3 different wavelengths. So why don't we make our independent variable that, and our dependent variable that, and so have D as a control variable, because I don't think it's very interesting moving the slits towards the screen and then lo and behold the fringe spacing changes as a consequence. I just don't think that's very interesting. So let's just make a note of what we're doing. So the first thing we're going to do is measure the diffraction angle for diffraction gratings for each value of n over d. We might not do all of them, but we'll do a whole bunch of them. And we use that in this equation to determine what lambda is. Notice I've put n over d rather than d over n because I want to get a straight line graph later. Then we're going to use that those 3 different lasers in the second, well, I've written here as the first equation, measuring W for each lambda, use that to determine S, and then we can just check what it says on the grating or even get the travelling microscope out to double check it. Let's draw a table of results. Right, that's going to be our first table. In fact, I might even use a spreadsheet for this because this will be quicker. 1 second. Right, I mean, there's actually quite a lot to do in this experiment, so I don't think I'm going to take repeats. Also, measuring theta is interesting because I'm not going to be able to measure theta directly. What I'm actually going to have to do is measure the distance along the screen between the orders and the distance between the slits and the screen perpendicular to the screen, and then use a little bit of trig. What I mean is we're going to have the laser doing this and the orders like this. We have the screen here like this. So if we measure these distances here and this distance there, let's call this big D. I mean, it is, isn't it? What should we call this one? I suppose we could even call this W if we wanted to be perverse. It's not W, but I'm going to call it W because it's so similar, same physics anyway. And so what's this diffraction angle going to be? Well, theta is going to be equal to the arctan of W over D. So I suppose actually on my table I can't put theta. I've got to put W and D, but I know what they mean. There we go. So on the table layout, we've got units. We can actually label what these are as well. It says this is the red one, so I'll copy this for the different colours. Oh, it's a horrible optical effect when you film a screen like this. So hopefully you can see it okay with all the weird colours. Anyway, WD, calculate theta from that, calculate sine theta from that. So that's all the independent variable. No, that's the dependent variable. That needs to be the other way around. Yeah. Let's move this around because we don't want that. We want independent variable on the left, which is that, and dependent variable on the right. Right, that's better. So independent variable, ND, calculating N over D. Then dependent variable WD, calculating theta, calculating sine theta. And then what we'll plot is, let's write this on a piece of paper. What we'll plot is, move this out of the way. What am I plotting? What I'll plot is sine theta. There we go. Sine theta on the y-axis equals n over d lambda. So we'll plot this on the y-axis, this on the x-axis, and that will be the gradient. You might not be able to see that green pen. N lambda equals d sine theta, rearranged. That's what we're going to do, so let's do it. We're talking for 24 minutes and we haven't actually done anything yet. So, laptop is there, ready for me to record my results. I don't want to use the green laser, I'm using the red laser. There it is. Get it turned on so I can see where the beam is pointing. There it is. I'm not going to bother with tape because we're measuring big distances. I'm not going to bother with the screen, I could just use an old wooden ruler. 300 lines per millimetre. Pop that in there. There it is. Position it so the spots are as symmetrical as possible, which is there. You could use a little bit of trial and error to figure that out. Still not quite happy with it. That should be more like that. There we are. We could get set squares out and all sorts, but that's fine. Ruler, measuring from there straight towards the 0th order, which is this one, the one that, as I was twisting the, I don't know if you can see that. Let's have a look at the camera. No, you can't see it. Let's just turn this like this. As I rotate the diffraction grating around, this is rotating it one way, this is rotating it the other way. You'll see that the spots, they kind of deform and move. And when it's most symmetrical, that's when we have everything lined up nice and straight. And the dot that didn't move, this one, that's the 0th order. So I'm going to measure to the 0th order to calculate what big D is, because that is going to be perpendicular to the slits and to the screen. We've got it all lined up properly. There we are. That will be perpendicular. So let's do that measurement first. Just move this back over here, so you can see the whole experimental setup. Move this camera down a little bit so you can see the whole experimental setup. Okay. Now it's more than a metre, which is a bit of a nuisance, so uncertainties are going to be quite high in this, but let's just do it anyway. Get a pen out. Not that pen, use this pen. So from the centre where the slits are to there is 1 metre, and then from there to the wall is another 77.5 centimetres. That's 177.5 centimetres for big D. I'll put that in. 177.5, so 1.775 metres. 1.775. Now the uncertainty on that is going to be plus or minus a centimetre at least. It's an absolute mess. But that's okay, that'll do. Now I'm not going to move my slit. I can even tape where my slit is down so that I don't move that if I wanted to. I'm just going to be careful not to move it. So let's look at the first order. So let's put n equals 1. D in millimetres is 1/300. I've got 300 lines per millimetre. So that's 1 divided by 300. And I can actually type that in as 1 divided by 300 into Excel, and it'll calculate what D is for me, which is quite handy. N divided by D, that's just a formula, so I can just type that straight in there, which in this case is 300, the first order N divided by D, which is 1/300 lines per millimetre, gives me N over D of 300, and the units of that will be millimetres, 300 millimetres. It's not a reflective ruler, so I can do this, it's fine. So the first order is 36 centimetres, or 360 millimetres. .36 metres. There we go. Then I'm going to do the second order. I might as well while I'm here. Because why not? I'm actually just looking and thinking I need to be more consistent with my units. I've got W in metres and D in metres, which is fine. N over D is in millimetres, so I'll end up with a wavelength in millimetres. So if I make N over D in metres, so I divide that by 1,000 to get it in metres, that's better. You can't see what I'm doing, I'm just doing some maths. Right, N equals 2, let's do the second order. I'm blocking it off with my shoulder. 76.7. 76.7. So N equals 2. 767. Can we get a third order? Yeah, we might just be able to get the third order. It's longer than a ruler, so actually I don't think there's much value in that, so we've only got to get 7 data points. So let's change D now. Careful not to move my slits. Let's change D to 1/600. It's about there. 1/600. So we're going to measure the first order for 1/600. I'll type 0/600, 1/600. Notice I'm entering data in real time. And that's the correct way to do it. You don't want to have to write the data in afterwards or copy it from someone else, because that would be a failure of competency 4. So W, as I've called it here, 76.5. I expected it to actually be exactly the same as last time. 76.4 actually. 76.4, never mind. 0.764. Actually, because the next slits, the 1,200 lines per millimetre, because that's going to cause W to be greater than a metre, I'm not sure I can reasonably do that. Not in any sort of sensible way. Yeah, where's that order? It's all the way over there. Everybody can see it. We've got an order all the way over there. I can't measure that with a metre ruler. That's what? It's more than 2. It's about 2 metres away, so I'm not measuring that. Oh no, I've only got 3 data points. Oh. Well, let's go back to the 300 lines per millimetre then, and see if I can. No, I can't get the third order for that. So actually, it looks like that's all I've got for the red one. 3 data points. Hey ho, that's what I've got. That's what I've got. So I've got my N/D here, and I've got my W and my D here. So I need to calculate my theta. So my theta is going to be the arctan, so the atan of, and it's going to be the opposite divided by the adjacent. The opposite was W, the adjacent was D. That's going to return, no, I haven't. No, I haven't. Okay. Yeah, arctan, I know what it wants. W divided by D. I'm being a moron. Right, so W divided by D, that's going to give me this in radians. If I want it in degrees, I can just type degrees into the formula thing as a function, nest the 2 functions together, and that'll give me my angle in degrees. Apparently degree doesn't exist, degrees does, so that was 11 degrees. Blah, blah, blah. Obviously, we don't want to use that many significant figures. I mean, 3 is probably plenty. Really, 3 would be plenty for this as well, but I recorded it to the nearest millimetre, so that is actually correct. But there we go. So then, in the angle over here, I'm going to do equals the sine of radians, because that's how Excel takes it. And again, we don't want that many significant figures shown, so let's shave some of them off. And now what we're going to do is we are going to plot, I mean, 2 of these data points are exactly the same, aren't they? These 2 here, and these 2 are the same. So this is basically a graph of 2 points, but we'll see what it looks like. So we're going to plot the graph. Here we go. I did say I didn't have very many points. So N/D, let's just check I've not plotted the wrong thing. N/D, yeah, I think before I said these 2, I meant these 2. So column C is plotted on the x-axis, and column G is plotted on the y-axis. So we've got the sine of the diffraction angle in degrees here and that. And we've got what's pretty much just 2 data points, which is a bit weak, but there we go. You can go into add trend line, and we can make the trend line look all pretty, make it black, and I don't know why Excel defaults with dotted lines, but it always does. We're not interested in that. We want to know what the gradient is. We can display the equation, and there it is. Let's make the text bigger. We should have a y-intercept of 0. We don't have a y-intercept of 0, but it's really close to 0. 0.0015. Extrapolate this back, it's not far off. It does suggest there's some sort of, maybe a systematic uncertainty, but with 2 points, we can't. It could just be a random error causing this, we can't tell. But there it is, that is our gradient. That is what we were interested in. That's better. I'd messed up my units at one point, so I noticed that the wavelength was supposed to be the gradient, and it didn't make any sense. The mistake I'd made was in here. So 1/300, that's in millimeters. And then I multiplied that by 1,000 to get it into meters, and then that then plugs into here to give me this gradient. I mean, the gradient is only giving me one significant figure, but it's the right order of magnitudes. There is actually a formula we can use in Excel to get the gradient, which is slope. Ignore that, it's just because the number doesn't quite fit in the space. So you can, oops, come on. Oh, you're not going to let me change the size of that? No, you're going to fuss with me? Quality stuff. Right, okay, equals... You won't even let me select these cells. Wow, Excel is really fussing with me. So equals slope, and then it's the y values, which are these, and then the x values, which are these, and that will return our gradient, which is 6.57 times 10 to the negative 7. In other words, we've determined that the wavelength of the red one is 657.5. Let's call it 657 nanometers, which sounds much more reasonable than what it says on the laser. So I just need to annotate this with wavelength equals, and all the calculations are there in Excel. Right, now let's do the other 2 colors, the other 2 lasers. So I'm just going to copy these sheets across. There we go, it's not calculating wavelength at the moment for either the green or the blue because I've just deleted all the data. Let's gather the data. I'm probably not going to bother plotting the graph for the green or the blue now because we've seen how to do it once, so I'm not going to bother doing it again. So green, switch it out with the green one. Which one's green? That one. Plop it in there. Grip it just tight enough to turn the switch on. Put it so it's nice and perpendicular like that. Quite coming up parallel to the laser. That's okay. Right, then it's 300 lines per millimeter. We're going to start with that one. Pop that one there. Twist it until it doesn't twist anymore. Twist it till it twists no more. Oh no, I've moved the... I need to measure D again. Right, let's measure D again. It's only an estimate of D anyway. Get a pen. It's 1 meter, and then 77.5. 1 meter, 1.775. The big D, 1.775. I'll put that in. Right. Let's measure N equals, making sure I don't turn around, so I don't want to look at the laser. My eye is dangerously close to being in line with the laser beam. 29 centimeters. While I'm here, I'll do the second order. 29 and 60.8. 29 and 60.8. 1 and 2. 29, so 0.29 and 0.608. I think it was 60.8. I'm going to end up measuring it again anyway. Yeah, 60.8. Oh, I can get the third one. Oh, I can get the third one, just 99. 99.2. 99.2. I've got the third order. Way! 0.992. There we go. D is the same for all of these. That's big D. Little d, this is 1 over 300. So I'm chucking that in straight away. N over d equals that, divided by that. I'm going to times it by 1,000 to get it in units of meters. Theta, let's calculate that again. So it's the arctan of, this time don't be dopey, the opposite divided by the adjacent. We want that in degrees because that's how we measure it. Actually, it doesn't really matter. We could leave it in radians in the table if we want because we're using Excel, so Excel can cope with radians if our primitive human brains can't. Equals the sine of, converted back into radians so that Excel can understand what we're doing. And it gives us already 544 nanometers for the green. But let's try the other diffraction gratings and see if we can narrow that down a bit, make it a little bit more accurate. So let's go with the 600 lines per millimeter. There we are, we're really motoring now, aren't we? Position it so nothing wiggles, like that. Just check I haven't moved anything. I have moved it, but what I'll do is I'll put it back exactly where it was so I don't have to remeasure D, because I don't want to remeasure D. Right, second order, 63.1 millimeters. So second order, 63.1 millimeters, 0.631. This is with D being equal to 1 over 600. Now I drag down a bunch of cells. And I increase the range for my slope calculation to include that cell as well. And that's the first order. Right, 544 nanometers. Can we get anywhere? I mean, I'm not going to be able to measure the second order with that one. How about the 1,200 lines per millimeter? Oh no, that's way over there. There's no chance. So that's the green one done. And I've got the wavelength of the green one now. The spreadsheet is giving me a number. Spreadsheet is telling me it is 544 nanometers. So, I'll leave that in the spreadsheet. I'm not going to bother writing that down. Let's move on to the blue one now. So, blue razor. Oh, there it is. Pop it in there. Close the jaws just so that it turns on. 300 lines per millimeter. Plop it in there. Position the slits so that it's at the same D as I had last time, because I really don't want to have to keep measuring it. Wiggle it around until the dots stop moving. This is all technical terms, of course. I have loads of orders there. In fact, I can't quite get the fourth order, never mind. But I can get the others. So we've got 21.9, 45.4. 21.9, 45.4. I'll try to remember two numbers. 21.9 and 45.4. I think that's what it was. Let's just double check. 21.9, 45.4, which is what? 45.1. 45.1 and 70.8. 45.1, 70.8. 45.1, 70.8. 708. And that's for order 1, 2, and 3. Then we've got 1 over 300 lines per millimeter. So that equals n divided by d times 1,000 to get it into meters. D is the same as we had last time, 1.775 meters. Before I do the calculations, let's just try the 600 lines per millimetre grating. Position it in the same place as the other one. Rotate it until things move no more. About there-ish. That should be the right place. Oh, that should be the right place. In principle, it shouldn't really matter where the laser is, as long as the slits are in the right place. I only get one order for this. Oh, it's at a funky angle, that's okay. 45.1. I've dropped it again. This is 1 over 600. 45.1. Exactly the same as we had before, actually. That's interesting. Do the calculation of theta. So theta is equal to the arctan. I'll put degrees arctan of the opposite divided by the adjacent. Do I want to accept that? Yes. Copy it down. And then equals the sine of radians of that angle. And as before, I want to use all the data. And the blue wavelength. The blue wavelength is coming in at about 413 nanometers. Now, I can check those later. I'm happy to check them. But I reckon the red is about 657 nanometers. I'm only going to go three significant figures. There's no point going higher than that. The green, I reckon, is 544 nanometers. And the blue, I reckon, is 413 nanometers. Now, we haven't done any sort of error analysis on this yet, which I ought to do. Now, I plotted a graph of, on the y-axis, sine theta, on the x-axis, n over d, and I ended up with basically 2 points, sometimes more, give me a straight line. If I want to find out what the uncertainty is, what I want to do is imagine a situation where that line is still acceptable, but as far deviated from the average. And I could go either steeper or shallower. I'm going to go steeper. So to make this line steeper, what we're going to say is we want to move this point down there and this point up there. So all the lower points, I want to say, what if n over d was the biggest it could reasonably be, and sine theta was the smallest it could possibly be? And these higher points, I want to say, what if n over d was the smallest it could possibly be, and sine theta was the biggest it could possibly be? Now, if I'm doing this on paper, actually, I'll just draw error bars and then draw a line. It's a little bit harder to do on the spreadsheet. So I'm actually going to create two new data points that I can say are within tolerance of my data that produce a new gradient. Future Keith here. I just want to show you, because I don't think I explained this very well, how we handle uncertainties when it comes to graphs. So let's suppose I've got a simple graph with 2 points, like you can see here. Well, we wouldn't want just 2 points on a graph, because that would not be very good. But let's just say that's what we've got. Our line of best fit is going to be some line which passes through, as closely as we can, passes through both those points. So it'd be something, using our 30 centimeter clear plastic ruler, like that. We want it to pass as close to the x's as possible for us to be convinced that that is the best possible line of best fit. And here it is, and we draw our line. Everyone's happy. So there's our line of best fit, and I might even label that LOBF for line of best fit, and we can measure the gradient of that and so on. Now, with these 2 points, you'll notice that there are error bars, and there are other lines that are not the lines of best fit, but they do pass through those error bars. So, for example, I position the ruler like this, and it passes within the error bars, and yet it's certainly not what we would call the best line of best fit. Now, sometimes this gets called the line of worst fit, but I don't think that's a very good description, because I think the line of worst fit would be that one. But anyway, I prefer to call this the worst possible line of best fit. It's a bit of a mouthful, but that's what we're saying, the worst possible line of best fit. Because each of these data points, it could be as high as this point here and as low as this point here. And this top point could be as high as this point here and as low as this point here, that actually this is also a possible line of best fit. It's just not the best one, it's the worst one. The uncertainty in the line of best fit will be the difference between the gradients of these two lines. Or I should say the uncertainty in the gradient of the line of best fit will be the difference in the uncertainty between these two lines. Now, in the case that we're talking about here, in some of them we had more than just 2 points. But the error bars were so large that as long as the end 2 points error bars encapsulated our worst possible line of best fit, then that was okay. So I sort of cut some corners, and in order to get an uncertainty in the gradient, I just used the extreme ends of the 2 points. So what that means is that, let's just get rid of my line of my worst possible line of best fit. What that means is I didn't bother plotting the error bars, although I will do later on. And I just simply said, well, what is the steepest worst possible line of best fit? So that is where this data point, I add the uncertainty from the y-axis and subtract the uncertainty from the x-axis, and I get a point over here which is within the error bars, if I could be bothered to draw them, for this point at the top. And I could do the same thing where I add the uncertainty in the x-axis but subtract the uncertainty in the y-axis. And now I'm going to end up being able to connect these two. Let's get the right pen. Oh, it's already got the right pen. Connect these two so that our worst possible line of best fit. And you can use the Excel formulas or whatever to calculate what the gradient of such a line might be. It doesn't, you can do whatever you want. You can draw it and then graphically measure it or what have you. But it's exactly the same thing. I just haven't been bothered to draw the error bars, probably because I was in a bit of a rush. I would want to lay it out more neatly if I was a student being assessed in this. Hoping that little side is going to help you. Now let's get back to the let's get back to the practical. I'm going to call those 2 points just point 1 and point 2. Right, so n over d. n over d for point 1 I want to make as big as possible, and for point 2 I want to make as small as possible. So I want to make this as big as possible. I can't change n, that's an integer. What about d? Well, I know that this is 1 over 300, and that's 1 over 600. But plus or minus what? I don't know. Now, it does say 1 over 300, 1 over 600. So I've got to assume the best. I've got to say that is 300 plus or minus, let's say, 1. It could be as high as 300.5. It could be as low as 299.5 lines per millimeter. But actually, I'm going to overestimate that uncertainty and say it could be as high as 301, could be as low as 299. That's what I'm going to do. So remember, on the x-axis, which is n over d, I wanted point 1 to be as big as is reasonably possible. It's that. It's not written in standard form, it doesn't matter. And n over d to be as small as reasonably possible for point 2, in order to make the gradient as steep as possible. Now let's look at the y-axis. So for point 1, I wanted the angle. So what I've done here is, with this one, I've added a centimetre, and with this one here, point 2, I've subtracted a centimetre from d, because that was plus or minus a centimetre. W, I reckon, was plus or minus a millimetre. It might be 2 millimetres. In fact, let's make that 2 millimetres, because it was a lot of guesswork of where the middle of that spot was. So let's make that 2 millimetres. And then that gives me my angles here. So now what I can do is, just as I did here, where I did equals slope of the g's over the c's, I do the same thing here, equals slope of the g's over the c's. That gives me my new gradient, and it's much higher, as we wanted it to. Now, the uncertainty is going to be the difference in those two. So 25 nanometers is the uncertainty. So my red, which is the one I'm currently looking at, is that I'd probably actually write it as 657 plus or minus 25 nanometers. I've now got uncertainties. And I'll do that with the green and the blue as well. And there we go. And the nice thing about using a spreadsheet is that took very little time, because I just copied the formulas across and tweaked them. So I've now got my wavelengths. I can look those up and check that they are correct, and that's my 𝗟𝗶5 done. We can now move on to the second experiment, which was measuring W for each lambda. Unfortunately, I now need to go to a staff briefing, so that will have to be in a second video, which I will either add to this one or just upload it as a second video. Right, fast forwarded in time, it's now 7 hours since the first part of the experiment, and we're ready to do the second part after a whole day of teaching. Here I've got the equation we're going to be investigating, and we've got, double check what we're doing with this, we've got the constant d over s, and we've got variable w, which we can measure, and lambda, which we have already measured. We've already measured the wavelength of these lasers with the uncertainties there. And we talked about how we get those uncertainties. Now, the S is listed on the diffraction grating, not diffraction grating, on the slits. S is listed as 0.1 millimeters. It's a one significant figure. I mean, I don't know how accurate this is. So we're going to measure S, or at least pull S out of this particular experiment, which means we're going to keep D constant throughout. We've got to make sure D is kept the same throughout as a control variable. So I'll put marks on the table where I intend to place the slits so that it's easier to do that. All right, let's set up the experiment. So you can see that here we've got our two slits illuminated with a laser, which is here, clamped as loosely as possible, just like before. And some distance away over here is the screen. Let's go get a closer look. Protective barrier here to stop reflections, and thank goodness it's there. There's the laser. There's the slits, and then all the way over there, we've got our diffraction pattern. And we can only really use these middle bits from perhaps there to perhaps there. And then it's dark after that. So we can only use those bits there. Now, rather than using our nice shiny vernier caliper in the laser beam, which would be tremendously dangerous, because it's going to cause all sorts of horrible reflections, we don't want that. So rather than doing that, that's reckless, we will draw on the paper and label it. We'll do that in a bit. First of all, I need to measure the distance. And just as before, this is going to have some considerable uncertainties on it, but the bigger the distance, the better the results will be, and the less significant those uncertainties will be. That's 1 meter. Crikey, have I put it in exactly the same place I had it before? Do you know I have? As if. That's exactly the same position I had it. The marker's still here on the table. That's exactly the same position I had it before. How about that? That's pure luck, isn't it? Well, what on earth did I have D as last time? I had D as, it's on my laptop, 1.775. It's exactly the same, 1.775 meters. Now that's give or take some loose 5 centimeters, possibly even 10 centimeters. What did I use last time? 10 centimeters last time. No, I used 1 centimeter last time. Oh my goodness me. I massively underestimated my uncertainties this morning. But okay, let's go with the plus or minus 1 centimetre. 10 centimetres is probably a bit much anyway. So I'm going to write down here 1.775 plus or minus 0.010 metres. And so there we are. There it is. I do like putting brackets around it so the unit applies to the whole thing. All right, let's measure W, the fringe spacing. So I'm going to use my pen. I'm going to come over here, and I'm going to start here, and I'm going to draw an R in the centre of each of these fringes. Because they're nice and large, I can do that. So there's a line down, and then an R, a line down, a line down, line down, line down. You do want to go centre to centre. Possibly that one, possibly that one. And I'm going to put an R under each one so that when I'm measuring distances, I know what I'm measuring. Now I actually only care about the first and the last one. So I'm going to draw a cross like that. And I'll show you what I've done. Well, this is one way of doing it. It's not the only way of doing it, but let's show you what I've done. So, my shadow there. So you can see, I need to label the R on this last one. But right in the centre of each of these fringes, I've drawn a line, and I've drawn a cross at the start and the end. I'll add a little R at the bottom of that one in a second. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 fringe spacings, and I can measure the distance from that cross to that cross with a ruler. It should be a straight line. It's pretty good. So that's the red one done. Now let's repeat it with the others. And I might as well do it on the same piece of paper. Taking the red laser out, and I'll replace it with the green laser. Which one's green? That one's green. So let's place the green laser in. And let's line it up. There we go. And we can see pure convenience. I haven't even moved the slits. I don't need to move the slits. But very fortunately, and it is a certain amount of luck to this, these fringes are now vertically in a different position to the red ones. So that's going to help. I can always line it up slightly differently and move things around so it's all on the same paper. But on this occasion, I don't have to do much lining up. It's already ready for me. So let's go and measure where the green ones are. Now this is a bit more tricky because I can't really clearly make out these fringes here like I could with the red one. So I actually think the middle of my green one is there. And then I've got green, 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 green. Green from there to there. And I can label each one with a G, not turning around. I don't want to get blinded with this horrible green laser. Might be a little bit relaxed when it comes to the red laser, which perhaps I shouldn't be. I'm certainly not relaxed when it comes to the green laser. It's a horrible thing. Right, now we're going to switch the green laser out. Replace it with, there it is, with the blue laser. And arrange it. It's right over the top, so let's just move it down a little bit. There we go. And there's our blue fringes. Get my pen out. Let's mark off the blue ones that I can see. So I can see that's quite a bit more faded. So let's go from there to there. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll label them with the B later maybe. I don't even think I need to label them. Don't really need to. But there we go. That is the blue fringes drawn. And you can see why I've chosen to discard the ones further than those crosses. They're just not that clear. And that's it. I can now turn the laser off. The dangerous part is done. While I'm at it, I might as well tidy some of this up. No, I'll do it later. Right, let's get get that down. Masking tape shouldn't remove the paint from the walls, but it apparently has. Well, it's not ideal, but the masking tape has actually removed the paint from the walls. Right, never mind, we'll ignore that. Hopefully the caretakers won't get too grumpy at me. Let's do some measurements. So here they are. These are our results. And we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10 lots of W, whatever that distance is, for the red one. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What are the odds? 10 lots of W for the green one. And this one is 1, 2, 3, 4, 5, 6, 7, 8, 9. Would you, Adam and Eve it? 10 of the W for the blue one. It's almost like I planned it. So let's measure these distances. I love the way you can see it goes red, green, blue, exactly as you'd expect. I'm going to use a vernier caliper. Start with the red, and I'm going to just line up as well as I can the ends with the middle of these crosses to the best of my ability. That's about as good as I'm going to do. And now I can read off this vernier scale. Luckily, I'm well practiced in this, despite the fact this is an awful vernier that's very shiny. I should, do you know what, let's turn the lights on so I can see what I'm doing. Oh, that's much better. Right, now let's read this in real time so you can see just how long it takes someone with old eyes like mine to read off a vernier. So it's more than 115 millimeters. More than 115, but how much more? It's 7/10 of a millimeter. 115.7. Which one was I doing? Red? Yeah, 115.7 millimeters. Okay, let's zoom in a bit. Let's do the next one. So taking this. Center of the green to the center of the green. Might as well do the green one next. Reading off this scale. It's not very easy to do, is it? Because it's moving around. So pause it, have a look at it yourself, see if you can work out what it is, and then I'll do it myself. So 90. Oh, the perils of old age with your eyes. 91, 92, 93.2. I reckon that's 93.2. Might be 93.3. I'm going to call it 93.2 millimeters. And now we'll do the blue one. Center of the X. Center of the X. So if you want to read along at home, pause this at the right time so that you can clearly see the two scales together. Right, let's have a look. It's more than 70. 71, more than 71. I think it's 71.9. Nearly 72, 71.9. Right, okay. Well, we're nearly there. We've just got to divide all those by 10, and I don't need a calculator to do that. I have the mathematical ability to divide by 10. I know, it's incredible. So, this one in here is going to be 9.32 millimeters. Oh, bum. Wrote it in the wrong one. Red is 115. I had the mathematical ability to divide by 10, which is hardly a brag, but apparently I don't know my colours. Right, green is the next one, which is 9.32 millimeters, and blue is the next one, which is 7.19. Okay, I've got my results. Let's get a graph. I could do a graph by hand, or I could just reach for Excel again. I'm going to reach for Microsoft Excel. Okay, this is my table from before. Let's add a new table. wavelength in nanometers. Might as well just keep the same unit. W in millimeters. Might as well just keep the same unit. Let's zoom in, or as I like to call it, bigger it. Hey, there we go. We'll type the numbers in. So 657, 544, 413. I'll worry about uncertainties later. 11.57, 9.32, 7.19. Put all the data in. Now we're going to plot a graph. We want to plot it so that wavelength is on the x-axis, and you never know whether the graph is going to come out correctly. You never can tell, because Excel does weird things. So move chart, new one, let's call it young slits. And we wanted on the x-axis the wavelength. We've got the wavelength on the x-axis. Great success. Only 3 data points, sure. Add a trend line. It's not bad, it's not terrible. Could be curved with 3 data points. It's hard to tell, isn't it? There's some things that we can do to make the graph slightly less poo. I've got a template stored, which certainly helps a little bit. I've got a few templates stored, but that one is the one I usually go with. But all the fonts are too small. There might be a clever way of selecting all the fonts at the same time, but I don't know it. So let's go into here and make it 20 so people can actually see it. Right, you don't want to see me messing around with font sizes. And there we go. There's our graph. Fringe spacing on the y-axis, wavelength on the x-axis. The gradient will be d over s, but we do have to watch out for units, because this is millimeters, these are nanometers. Well, millimeters are 1,000,000 times bigger than nanometers. So we do have to watch out for this. Whatever our gradient is, we have to divide it by, I think it's divided by 1,000,000. We'll figure that out in a bit. I choose to view the equation for the straight line. Doesn't pass through the origin. It's not far off, but it doesn't pass through the origin. So there's uncertainty somewhere. Not surprised. And then we've got this quantity here. Right, let's see if we can calculate S from this. So if we want our gradient to have no dimensions or anything like that, I'm going to write down here, and I'll show you what I've written in a minute. Gradient equals, and then it's 0.0179. But what is this? Well, this is milli divided by nano. So that's times, milli is 10 to the negative 3, divided by nano is 10 to the negative 9. So you can have a look at what this says there. That's the gradient. And it's got no units, because that will now be meters divided by meters. So this is millimeters divided by nanometers, which is the unit for that gradient, which is equivalent to 0.0179 times 10 to the 6. I think I said times it by 1,000,000. I might have said divided by 1,000,000 before. Who knows what I said? But that is the gradient. That is correct. And that is equal to d divided by s. We want to calculate what s is. So s is going to be d, that's 1.775, divided by this gradient, 0.0179 times 10 to the 6. Let's go get a calculator. Once again, I find myself using this horrible thing. Casio thing. It's awful. Okay, 1.775 divided by, let's do it as a fraction thing, 0.0179 times 10 to the power of 6. So about, it's not far off. Let's just write that down. 9.916. No point having that many significant figures. So let's call it 9.92 times 10 to the negative 5. And that would be in units of meters. Okay. I'm actually quite happy with that, because if we type in 9.92 times 10 to the power of -5 into the calculator. The calculator can do something really quite clever. What you can do is you can use engineering display mode. Let's get it as a standard form answer. You can use the engineering display mode. So you press eng, and it gives you powers of, thousands. So 10 to the -3, 10 to the -6, 10 to the -9, and so on. So you can cycle through these like that, or cycle backwards through them like that, to see what the number is with these more sensible orders of magnitude. So 10 to the -3 is milli, so that is exactly the same as 0.0992 times 10 to the -3 meters, or 0.0992 millimeters. Well, we were expecting, just a reminder, oops, zoom out. Come on, zoom out. We were expecting 0.1. We got 0.0992. Yeah, that's not bad. That's not bad at all. But we don't know whether this lies within the uncertainty of this. So we have to do some error analysis. We haven't got a choice. Now, we're going to do the same thing we did last time. We've got our graph, and we are going to add error bars and see what a reasonable line could be that passes through the error bars, but as badly as possible. Worst acceptable line of best fit is the way I like to word it. So let's add those error bars. I've added a column for the uncertainty in the wavelength. As for the uncertainty in W, that's going to be quite hard to judge, because the instrument I was using measures to the nearest tenth of a millimeter. And then not only that, I divided my separation of 10 fringe spacings by 10. So I don't think there's any significant, I don't think the uncertainty from this is significant compared to the uncertainty in this. So I'm going to effectively discard the uncertainty in W. I just don't think it's big enough for me to be interested in. So let's add those uncertainties to this graph, and yeah, we've got to try and figure out how to do that again, and every time I forget. So error bars, and then where are we going in this? Let's put standard, and I'll change it later. The fringe spacing error bars I don't want. So if I go into here, oops, I accidentally deleted them. I go into here, go to format error bars, and in here somewhere I should have, where is it, error bar options. I've got error bars in the X direction, error bars in the Y direction. So error bars in the Y direction, it's just 0. In fact, I might just delete them altogether. But error bars in the X direction, have I accidentally deleted them? Oh, I've deleted them as well. Right, let's put them back. Error bars in the Y direction, fixed value 0. I don't have any errors. Error bars in the X direction, let's do those. And this is going to be custom, specify value. We're going to go looking for them. So it's going to be them. The negative is also going to be them. And for whatever reason, they've decided to color them in so there's no line, which is irritating. Anyway, there we go. So we now have our error bars, and you can see those there for our, zoom in a bit, so that might help. We've got our error bars for the wavelengths. So now the worst acceptable line of best fit. Looking at it, because we're just passing through this is going to be a bit trickier to draw. So let's try a few. So there's a trend line that passes through these extreme error bars, but it doesn't pass through that point. So that's no good. Let's try another one. Okay, so this line of best fit passes through that error bar, but it misses this. So it needs to be a little bit shallower than that. And there we go. So we pass just through the right-hand side of this error bar, comfortably through there, and then, well, not comfortably, just on the left-hand side of that one. So right-hand side of this, left-hand side of that, and then it passes comfortably. That was the school bell. right-hand side of this error bar, left-hand side of that error bar, then comfortably through there. And that is a line of best fit that passes through the error bars, and therefore it is acceptable, but it's the worst one that you could draw. And the way I did that is I took each of those wavelengths and I subtracted the uncertainty and added the uncertainty, subtracted and added for each of the wavelengths. And then I simply picked the values that correspond to produce a line. Now I could now go equals slope of the known y's and the known x's. That's going to give me my new gradient. And if I go back to my working, zoom out, go back to my working, I've got a gradient of the worst, the worst acceptable line of best fit, which I can write down here. So I'm going to put down here worst gradient. And that was 0.0195. But remember the units of that, 10 to the negative 3 over 10 to the negative 9 meters per meter. So that gives me 0.0195 times 10 to the 6. I'm going to pull out my calculator here, because what I'm going to do is I'm going to calculate what that upper bound S would be. So S upper is going to equal 1775, and in fact, no, because it's plus, the upper bound one is going to be plus 1 centimeter, so 1785, so 1.785. I'll put that into the calculator. That's my D, so 1.785 divided by my gradient, which is 0.0195 times 10 to the 6, like that. So fraction, ugh. Oh, it's horrible. Ugh. Engineering, go back the other way. There we go. So this gives me 0.0915. I want the maximum deviation. I should probably go with the smallest value of D for the biggest value of W. Smallest value of D, biggest value of, sorry, not W, the gradient. Smallest value of D, biggest value of gradient would be giving me the most deviation. So let's not do that. Let's say SU, it's not even the upper, it's the lower, so I've got that wrong, but it doesn't matter. 1.765, so I'm subtracting 1 centimeter from this. Let's get the camera positioned better. Subtracting 1 centimeter from that, divided by my gradient, so that is 0.0195 times 10 to the 6. Right, let's try that. 1.765.0195 times 10 to the power of 6. And there we go. So this is the lower bound, not the upper bound, is 0.0905 millimeters. And the difference between them will be the uncertainty. So we can say 0.0992 subtract 0.0905. Well, we might as well stick it in millimeters, is 0.0087. So my S presented with an uncertainty is 0.0992 plus or minus 0.0087. And the units are millimeters. That's the uncertainty in that. Notice it's a two significant figure uncertainty because that's what the exam board wants for some reason. And we've matched the number of decimal places between the uncertainty and the average number. So there is our S. is 0.1 within that range? Well, let's find out. So 0.0992, add that uncertainty. Yes, that gives us, as you can see on the calculator, zoom in, that gives us an upper bound of this of 0.1079 millimeters, which is indeed, 0.1 millimeters is indeed within that range. And so there we have it. We have measured S. Now, we could go a step further and get the traveling microscope out to measure it, check it. And as I said before, if we wanted to get our our competency 5B, we've got to do some research. What are we going to research? We'll probably look these up and see whether these values are similar to what we might expect. But we're reassured by that. So that is the experiment RP2 done.